Hello everyone, welcome to this Module 2 crash course. If you've watched the Module 1 crash course, you would understand that in these mini crash courses, I attempt to go through the entire module in approximately 2 hours. I don't really stop for questions, well, obviously not questions that you might have at home. I'm referring to questions in the concept check as they appear throughout the booklet. If anyone has any questions, by all means, you can message me afterwards or when you obviously receive this. But without further ado, let's just kind of jump in. So module 2 is dynamics. Module 1 was kinematics, as we all know. Now, dynamics and kinematics are very similar. Kinematics is often referred to the study of motion with force, without reference to forces, sorry. And dynamics is the study of motion with reference to forces. So you can imagine that we're going to be dealing with forces this module, and we're going to be looking at things such as Newton's laws and all interesting consequences that arise due to that. So here we can see the lessons. So firstly, we can see the first dot point where we have to talk about Newton's laws and describe static and dynamic interactions between two or more objects. So firstly, let's kind of explain some things. So what does static mean? It's going to be very important that we define this later on. Static just generally means stationary, whereas dynamic, as we can imagine, is going to be moving, as I kind of referenced it earlier. So firstly, what is a force? Now, we will get to the quantitative definition of a force, but for now, all we need to kind of know in terms of quantitatively is that a force is a push, pull, or twist. We'll obviously get to the mathematical definition of force, but for now, this will suffice just to bring everything up to speed. So if we remember from module 1, we had things such as scalars and vectors. Now, force is a vector quantity, and we all know it's measured in newtons after Isaac Newton, and all vectors have direction and magnitude. And here we can see some examples of forces that we see in our everyday life. So if we push a stationary lawnmower with enough force, it begins to move. If we push on the brakes of a moving bicycle, it slows down, so it decelerates. But remember, deceleration is technically acceleration in the negative direction. And if we apply enough force to an aluminium can, such as a Coca-Cola can, etc., we can change the shape of the can. And in general, this is kind of hinting at the actual definition of a force, but we can just assume that a force is going to cause an acceleration. And we can see that all accelerations and obviously decelerations, because a deceleration is just an acceleration in the negative direction, are caused by forces. Now, there's two types of forces. The first one is obvious. It's the contact force. So if I were to clap my hands, I won't do that because the microphone will probably die. But I'm exerting a force on my hands. If I were to, I don't know, punch a wall, I'm exerting a force on the wall through contact. But the other thing that we have to consider is something called non-contact forces. And well, what exactly is a non-contact force? Well, you can imagine very simply that it's just going to be a force that causes an acceleration, but there's no contact. And the biggest example is gravity. So gravity is obviously an example of a non-contact field, because if I drop an apple hypothetically, the Earth doesn't have to touch the apple for the apple to accelerate towards the Earth. And as such, we have a non-contact force. There are two other non-contact forces in the universe, and they are the electric and magnetic force. We'll learn much later on, probably in year 12, that these are actually one and the same, the electromagnetic force. But for now, we know that if you hold two charges of the same, well, polarity, so these are both positive, they're going to exert a repulsive force. And it's the same thing if I have two north poles of a magnet. There's two north poles, they aren't touching each other, but they repel each other. And it's the same if we had two positively charged particles. So now we're going to move on. So we're going to look at the relationship between force and acceleration. I know I skipped this idea, does every force cause an acceleration? And the short answer is no, you can read if you want. But we're going to see this relationship when we plot force and acceleration. So an example of this would be, hypothetically, let's say I have a machine, and this machine can exert 1 Newton, 2 Newtons, 3 Newtons, 4 Newtons, etc. And let's say I have a cart that is 1 kilogram. We can see where this is going, F is equal to ma. But if we were to do an experiment and we could measure the acceleration of this car as more and more force was applied to it, we can very clearly see, and we would obviously get acceleration through one of the equations. In particular, we can just have A is equal to V minus U on T, so delta V on delta T. And we'd actually see that, well, we wouldn't get an exactly straight line, but we would get a line of best fit that is straight rather. And this graph can tell us a lot of interesting things. The first thing that it can tell us is that acceleration does not happen immediately, and that there's actually a certain amount of force that you must start applying before you get an acceleration. And the reason for this is because, well, there's things that we have to overcome, such as inertia and friction. And right now, I encourage you to do the same. If you're sitting at a desk, try to push the desk. You'll realize that there has to be a certain amount of force that you exert on the desk before it starts to move. And then the second thing that we realize is obviously through the line of best fit, and that the acceleration is directly proportional to the force applied. Now, what does proportional mean? Well, mathematically, this is denoted by an alpha symbol. So we're going to have force is proportional to m. And all proportional means is that as the left side increases, so does the right side. So I could have A is proportional to B. If the left side increases, which is A, that means the right side would increase, which is B. So basically it's saying is that as F increases, M would increase as well. I hope that makes sense because we're going to be applying this notation soon. Okay. So if we were to plot the relationship between acceleration and mass, and also please note, it was implicitly mentioned in this prior example, but I said that m of the cart was 1. And what that means, and I see I made a mistake, F is proportional to A, not F is proportional to M. Well, technically is, but not in this example. I set A, or rather M, is equal to 1 kilogram, because that made things very easy. We had a nice straight line. But all I'm trying to say is that the mass is constant. Now, I'm going to jump ahead of here, and I'm just going to point out that F equals ma. Wow, shock and horror. But why would I keep m constant in an experiment? Well, there's obviously a bunch of reasons for this. The short answer is, well, there's 3 things in the formula. I have to have an independent variable and a dependent variable, and everything else has to be controlled. So remember, we're changing the F, we're measuring A, so therefore M must be constant. And then otherwise the scientific method doesn't work. And the second big reason is that M being constant is a condition in order for proportionality to work. So in order for F to be proportional to A, M must be constant. And that makes sense because, say hypothetically, F increased, but A decreased. that I'm trying to measure, say F increased, but the mass was getting smaller, well, how can I accurately measure A? What's the relationship between F and A if F increases and M decreases? Can we see how it just becomes too convoluted? So we like to set M is constant in order for this identity to hold true. In a similar fashion, we can see here that, well, I'm changing the mass of the object and the acceleration is being measured. So we can see that F is constant. And an example of this would be, like, say I'm flicking something. Say I can, and this logic holds, like say I flick a ping pong ball. Now a ping pong ball doesn't have a lot of mass. And we can visualize that when I flick a ping pong ball, it's going to fly off very quickly. So that would be about here. Low mass, high acceleration. And the converse would also happen. So let's say I was trying to flick a chair on wheels. Now that chair on wheels will move if I flick it with the same force, but it's not going to move as fast as the ping pong ball because it has more mass. And that can be denoted here, for example. It doesn't actually matter. The point is low mass, high acceleration, high mass, low acceleration. And hang on a second, this isn't actually a straight line. So what gives? Well, this is actually an example of a hyperbola in mathematics, as we all understand. But whereas in the previous example, we said F is proportional to A, we say that A is inversely proportional to mass. And all that simply means is that, well, by our notation earlier, if this side increases, excuse me, I don't know why I'm having difficulties. This side would also increase because as the left-hand side increases, the right-hand side increases. But the question kind of remains, how do I make 1 on M bigger? How do I get that bigger? Well, in mathematics, if you divide a number by a smaller number, it actually forms a bigger number. Now that doesn't actually make sense, but an example would be this. So we have 1 on 2 versus 1 on 0.2. Now this is obviously equal to 0.5, but if you were to type this into your calculator, you would actually get 5. So what actually happens here? Well, although as A increases, 1 on M increases, if A increases, M is actually going to decrease to make 1 on M bigger. So that can be interpreted in the inversely proportional idea, because if it's inversely proportional, that means that if A increases, then M has to do the opposite because it's inverse. So M would actually decrease. And there's another final application to this, and this might be a little bit confusing right now, but technically A is proportional to 1 on M, because as the left side increases, the right side increases. So A is proportional to 1 on M, which means that if I were to plot a graph of 1 on M versus A, I would actually get a straight line similar to this previous one. But don't worry too much about that. It's just a mathematical trick. You will have to do graphs like this in the future, but I'm not too concerned about it now. This just serves as an introduction to the quantitative nature of forces. Okay, so now that we finally have all of that out of the way, let's actually talk about Newton's laws. So we know what Newton's first law is. Hopefully we all remember it from year 10 physics. But Newton's first law states that an object tends to stay at rest or in motion at a constant velocity unless acted by an unbalanced force. So what this means is that an object is going to stay exactly how it is until something else disrupts them. So we have an example. We have an example here, and I recommend that you do this example. But I'll just like to provide examples of where Newton's first law holds. So an object stays at rest. So if my car is parked in my driveway and I do not put a force on it, the car's obviously going to continue to stay where it is. But as soon as I apply a force on the car, whether it be me starting the car and driving off or pushing it hard enough without the brakes on, the car's obviously going to move, and that's because I exerted a force on the car. Now, an example where an object will be in motion will stay at motion unless I acted on by an unbalanced force will be something like an ice, like a hockey puck on ice. Now, we know that because, spoilers, ice doesn't have a lot of friction, has a low coefficient of friction, the hockey puck is going to generally continue sliding in its direction until it eventually slows down because of things such as friction or if it hits a side wall, etc., etc. Something that you may have heard in reference to Newton's first law is inertia. But what is inertia? Now, it's very, very important that we don't actually state that Newton's first law is inertia. It actually isn't. Newton's first law is related to inertia. What is inertia? It is the tendency of an object to resist a change in motion. It is not a force. What inertia is try to push something heavy. It is very hard to make that initially move. Now, you could chalk it up to, it's friction, but it's also inertia too, because an object will stay where it is or will keep doing what it's doing unless an unbalanced force acts on it. So we can see that inertia is purely dependent on an object's mass. So it's harder for an acceleration to act on these bodies of greater mass. And what is an acceleration? Well, if we remember from module 1, an acceleration is an increase in speed, a decrease in speed, well, velocity rather, because acceleration is a vector, and a change in direction, because the direction of the velocity will change and that results in an acceleration. Okay, so we have a concept check here. I'm just going to go through the questions very quickly. I really recommend that you go through this concept check, and I will reconvene with you in about 30 seconds. So just pause the video right here and just attempt the question, and then obviously we'll get back to it. All right, I'm back. All these questions should be pretty straightforward. There really is no mathematical questions. It's just about understanding what is a force and applying ideas that we've learned. So state Newton's first law. I hope that was obvious. Inertia, once again, descriptive, qualitative force question, relationship between mass and acceleration. We know that they're inversely proportional. Draw the graph. And then force and acceleration. We know that they're directly proportional. And once again, you can draw the graph. And 6, I touched on very briefly. Okay, So we're going to start getting into, well, the applications of force as a vector. Now, you'll probably notice I actually haven't given you Newton's second law yet. And the reason why I haven't given you Newton's second law is because a lot of, well, first reason is that the syllabus insists on doing all this stuff first. But the reason is last module we focused a lot on dealing with vectors. Now we do vector analysis. We would resolve vectors, we would find the resultant vector, we would do things such as relative velocity where we had VA minus VB and would have to find the resultant vector from that. And so I understand the vector principles that this module is trying to teach, which is very good. So just like how we can add vectors such as velocity, displacement, etc., we can add force vectors. And we can have things such as the resultant force. And the resultant force is explained or denoted mathematically by sigma F. And what sigma means is that it's the sum. So it's just the sum of F. And this is just going to be force A plus force B plus etc., etc., etc. I like saying that a lot. But what is equilibrium? Well, equilibrium is very interesting. So if the net force acting on an object is zero, which means that all the forces acting on an object cancel out, then according to Newton's first law, the object's velocity will remain constant because there's no force acting on it. If this is not the case, then obviously the net force, or the resultant force, we can use those terms interchangeably, is going to be the direction of the force that the object experiences and obviously the subsequent acceleration. So what we can do is we can literally, and as you can see here, we can add the vector components together. We can draw the resultant using Pythagoras' theorem if it's a right angle triangle, or through the cosine rule, calculate the magnitude of the resultant, and using right angle trigonometry or through using the sine rule, calculate the angle and hence the direction of the resultant. So an example would be this, right? So I can clearly see that if I draw the resultant, well, the resultant is just going to be 25 minus 25 because it's in the opposite direction. And so my net force is going to be 0. And so I'm going to be in equilibrium. And we can see these words again. Static equilibrium is going to be when I'm in equilibrium, but I'm stationary. And dynamic equilibrium is going to be when I'm in equilibrium, but I'm moving. Now, all this means is that because all the forces cancel out, we know that through F equals ma, we haven't explicitly stated it yet, but if F equals 0, then A equals 0. And if A equals 0, then that means that my velocity is constant. My velocity is not changing. The most famous and, well, not necessarily famous, but the most recognizable idea of equilibrium is something called the normal force. So let me pose you this question. So hypothetically, let's say you were standing. What are the forces that acts on you? If you're not moving at all, just standing completely still, no forces acting on you from the left or the right. But we spoke about a force earlier briefly, and it was a non-contact force. And that non-contact force is gravity. And that gravity is obviously mg, the weight force. It's an acceleration due to gravity. But this doesn't really make sense because if I just had a downwards force of mg, that means that I would be constantly accelerating to the earth. Like I would slowly become squashed as I slowly get crushed by the force. But this actually doesn't happen because there is a force exerted by the Earth's surface. And this kind of leads into Newton's third law. And Newton's third law, it's in here, but I'll just quickly give it. It's for every action force, there is an equal and opposite reaction force. So if mg is pointing down, that means that there has to be a reaction force, which is going to be n, the normal force. And this is why we don't actually move, despite the fact that we have an acceleration acting on us, which is the acceleration due to gravity. So we can read here. Yeah. So we see the weight of force of gravity is acting on the body. But however, as the body isn't accelerating downwards, but is rather stationary, this implies that the body is in static equilibrium because it's not moving. But we know that in static equilibrium, all of the forces must add to zero. So there must be an upwards force, and this upwards force is the normal force. So just note that the normal force is the reaction force to gravity, even though we haven't explicitly spoken about Newton's third law yet. Okay, so you have a concept check here. Just pause the video here, and in 30 seconds, I'll come back and we'll kind of quickly go through the ideas of this concept check. All right, I'm back. So basically this entire concept check is just looking at, well, vector diagrams. So we can see here a 15 Newton forces acting towards the left and a 12 Newton forces acting to the right. Calculate the net force. Well, if this is my box, this is just my generic object, just a box, we can see that we have 15 newtons and we can see that we have 12 newtons. So if we have 15 and 12, we're going to have, well, plus, we're going to have 3 newtons to the right. And this is because sigma F is equal to force A plus force B, where force B is in the opposite direction of force A. So they cancel. Someone might be rolling their eyes right now saying like, oh, well, this is obvious. Why are you kind of explaining this? And the reason why I am explaining this is because it becomes very complicated for when I have vectors in multiple directions, which I think is the last question in this concept check. Yeah, so here we see we have 12 newtons down, 2 newtons up, and then a 5 Newton force going from right to left. So 5, 2, and 12. Well, remember, is equal to force A plus force B plus force C. And we have to add all these tip to tail. So I'm going to have 12 plus 2 and then plus 5. So obviously this is a very sketchy drawing. You do you, whatever works. But here we can clearly see that the 2 will cancel with the 12. So that's just going to create a triangle, a right angle triangle, mind you, where this is going to be 10. This is going to be 5. You'd use Pythagoras' theorem to solve this. And then last but not least, everyone forgets this. It's a vector. You must calculate the angle using inverse tan. Now, some people ask me, but what is that angle in reference to? Like in module 1, we had north, east, south, and west. But here, there is no north. So what do we kind of do? Well, the way we kind of address it is that we always talk in relation to the x-axis. So if I say this is the x-axis here, right? The angle is actually going to be alpha. So what I'm saying is that you'll calculate theta, and then you'll do 90 minus theta to get alpha. And so the angle would be alpha degrees, or just alpha degrees, below the negative x-axis. Because very simply, if this was a number plane, we can see that this would be the negative x and this would be the positive x. And we can see that the angle is, well, is that. So if we're from the negative x-axis and we move theta degrees below, we're going to get to the direction of what our net force is. I hope that makes sense. If you have any questions, please ask me, or just by all means. There are many questions in this booklet, and I highly recommend you do as many as you can. And then for question 4, once again, we can clearly, well, not clearly, but this harkens back to what I said earlier, where some people might find this redundant, where they're like, oh, well, duh, obviously I'm going to add force, like obviously these two cancel, so I don't have to do the whole force A plus force B plus force C. And the reason is when you get dealt with questions like these. So for questions like these, I'm not giving you nice left, right, up and down. I'm giving you up, right, and then 100, and then what's that? South 10 degrees west, and then yeah, I don't even know what this one is, but you have to think intuitively and say, well, how am I going to break this up? And that's where you would obviously do vector analysis and work through the heavy math, and it would all come out. All right, we finally get to Newton's laws. So Newton's second law, so if we essentially combine these two, remember in this one we're dealing with F is proportional to A and A is proportional to 1 on M, we can clearly see that if we link these two together, we're going to get A is proportional to F on M, which means that F is proportional to MA. But that's just Newton's second law, so we could just say F is equal to MA. And where the units of force are in N, but are also in kilograms meters per second squared. Because remember, units, I'm technically timesing mass and acceleration together. So I'm timesing M, which is kilograms, by acceleration, which is meters per second squared. Hence, 1 Newton is 1 kilogram meters per second squared. All right, so that's just F equals MA. And all we're going to be doing with this newfound knowledge that we apparently didn't know is we're going to be resolving forces into the components because, well, they're vectors and we can do that. And the other thing is that we're going to be dealing with actually finding accelerations now. So if I have a net force, I can hypothetically calculate the acceleration that the object is experiencing, and then I can use one of the Suvat equations, which is v squared equals u squared plus 2as, v equals u plus at, and s equals ut plus half at squared, to find maybe where the object will be in 20 seconds or so. Things like that. But just remember, this is cos theta, so f cos theta, and this is f sine theta. Please do not please do not mix up sine theta and cos theta. You will lose easy marks, and it's honestly heartbreaking sometimes to watch this. Okay, so we have another concept check. Just pause here, and I'll be back in about 30 seconds or so. Okay, I'm back. So question 1, 2 are very straightforward. Question 3 talks about friction. We haven't really spoken about friction, but I like to define it. So friction in a nutshell, it obviously comes up later, but it is just a force that opposes the motion of an object. So if I have a 10 kilogram cart and I'm pushing it with 35 newtons, friction acts in the opposite direction. So it says here, acts in the opposite direction of motion to the crate. So friction is going to be acting in this way. And well, in this question, it states that I have a acceleration, a net acceleration of 2 meters per second squared, which means that by F is equal to ma, I must have a net force of 2 meters per second squared times 10 kilos, which is going to be 20 newtons, which means that this force plus this force must equal 20 newtons. So obviously friction must be 15 newtons to the left. Please state the direction. Question 4 is a very similar question to question 3, so I'm not going to go through that. And then question 5 is a very interesting question. Yeah. So for question 5, we have forces acting at different angles. So we see here, once again, I have my generic object, which is a box. A 200 Newton force is acting at an angle of 60 degrees. When it just says 60 degrees without any direction, we always assume that it is above the positive x-axis. So it's just like that. So that's 60 degrees. And so this is 100 kilograms. So this is So this is 200 newtons. And then a second force of 100 newtons acts on the same force at 30 degrees in the same direction. So I probably should have made this bigger, but oops. So this is going to be 30 degrees, and then this whole thing is going to be 60 degrees. So it's asking, what is the net force and acceleration of the object acting in the x direction? So we're not actually asked to find the net force. We're not asked to find what is this force plus this force. We're only asked to find what is the sum of their two x components. And we can very easily do this because we have the magnitude and the angle of the force. So we can just resolve it. So we can clearly see that this is going to be 200 newtons. And once again, it's right angled because, well, 60 degrees. It has to be right angled because we're acting on a flat surface. And then, well, this very similarly, we are going to get this. Oh, that didn't work. Interesting. Anyway. And when it's asking to find the sum of the forces in the x direction, well, it's just going to be this force plus this force, 1 plus 2. And we can clearly see that 1 is just going to be 200 cos 60 plus 100 cos 30. And that's going to be equivalent to the net force. And then, well, how do we get from force to acceleration? I'll let you guys figure that one out. But we're just finding the x direction. So we have this force. What is the x component? Well, it's going to be the adjacent side for both of them. Very simple. We've covered this in module 1, except with the added note that F equals ma to get an acceleration. Okay, so the last thing is Newton's third law. So we kind of touched on it in regards to the normal force, but what is Newton's law? Well, very simply, it is to every action there is always opposed and equal reaction. or the mutual action of two bodies upon each other are always equal and directed to contrary parts. That's a bit of a mouthful, but what does it mean? Well, let's take a look at an example. So if I were to throw a ball at a wall and that ball was to hit the wall, we know that the ball bounces off the wall. But let's say that this wall was on wheels, so it could move, like it's on like a skateboard or something. It's like a big fridge on a skateboard. What it's saying, what Newton's third law states, is that if the ball strikes the wall, Newton's third law states that the ball pushes on the wall with the same force that the wall pushes onto the ball, which is obviously this formula. I just replaced A with W and, well, for wall, and B is ball. But what about that negative? Well, that negative just means opposite direction. So it's saying that when the ball hits the wall pushes back on the ball with the same force. But then we know that if this wall was on a skateboard, hypothetically, it wouldn't move as far away or as quickly, so it wouldn't have a higher acceleration than the ball, because the ball would just go flying off the wall, but the ball would just like barely move if it was on wheels. So it's important to remember that, well, force is equal to mass times acceleration. So if the force WB is equal to minus FBW, this is going to be little m big A for the ball. No, other way around. This is going to be big M little a for the wall, and this is going to be little m big A for the ball. Right the first time. Far out. Yeah, because these forces are equivalent, but the masses aren't equal, and hence the accelerations will not be equal. We know that the ball has a much smaller force, and as such, it will have a much higher acceleration than the wall. And that comes back to the idea that A is proportional to 1 on m. So as A increases, m decreases when F is constant. And we can see once again, everything is linking together. Okay, we have another concept check. So I'll give you guys about 30 seconds or so, and then obviously we'll come back to this. Just pause now, please. All right, cool. I'm back. So this concept check isn't too hard. The only question I would like to draw attention to is question 3. So a cat of mass 5 kilograms jumps on a dining table of mass 30 kilograms. As the cat walks around on the table, what is the average force that the table applies to the cat? So this is obviously a Newton's third law question, because the cat... do I really want to draw a cat? Apologies for a bad cat drawing. So that's the table. As the cat walks around the table, the cat is technically exerting a weight force on the table. So the average force that the table applies to the cat is going to be the same force, but in the opposite direction. And this is the normal force. Because through Newton's third law, for every action is an equal and opposite reaction. So that means that in order for the table to apply a force on the cat had to originally been applying a force onto the table. And what is that force? Well, that force is just weight force. And I haven't really spoken about the weight force much, but just to recap, the weight force is given as F is equal to mg. because m is mass and g is the gravitational acceleration. Now, g is 9.8 on your formula sheet. But anyway, so we're going to have 5 times 9.8, which is 49 newtons. And we can see that the normal force must be exactly equal to the weight force. So we can see here that force table on cat is going to equal to the normal, which is going to equal to 49 newtons. And yeah, all the other questions are very similar. But once again, if you have any questions, please message me regarding this. Okay, so we're going to start the second lesson, and in this second lesson, we're looking at non-conventional forces to set up inclined planes. So what is an inclined plane, you might ask? Well, it's just a type of question that requires a lot of force understanding. So let's get this understanding out of the way first. So firstly, friction. We've spoken a lot about friction, but very briefly. So we know that friction is just a force that opposes motion. So if I have a box and that box is moving to the right, friction, which is denoted by little f, will point to the left. And the reason why friction is little f is because if we use the capital F, we'll obviously get it mixed up with the regular force, and then hence huge complications would ensue. There are many ways that friction are caused. These are the 3 main ways. If you're interested, please read about them. It's very interesting. But the only one that we really care about is surface roughness. And the measure of surface roughness is called the coefficient of friction. And we'll see that very soon. So the reason why friction exists is because back in our acceleration force experiment, we realized that there's a certain amount of force that you must apply in order for an acceleration to occur. And as I said earlier, push on your desk. You'll realize that there has to be a certain force that you use in order for the desk to start moving. And one of the reasons why this is so is because friction must be overcome before the object can move. So we can see this in this example. I personally prefer pushing the desk, but we can see here that the same idea holds. Once the applied force exceeds friction, the box begins to move and we have our acceleration. But that's an interesting question because obviously I need to push more. Obviously my pushing force has to be greater than friction in order for the box to move. But when the box is moving, there is still friction opposing it. Because in the case of like a trolley, for example, if I were to push that trolley and just let go of it, the trolley would obviously slow down. So there's friction in order to push the object, and then there's also friction when you're pushing the object. And the answer to that is that there's actually 2 types of friction. We have static friction and we have kinetic friction. These types of friction, they kind of occur all the time. So we see here which type of friction must be overcome to make an object move. Well, that's going to be static friction because it's the friction that causes an object to be static or stationary. And then which type of friction opposes an object once it's moving? That's obviously going to be kinetic friction because it's moving, kinetic. So friction, I denoted it as FF, but I just personally prefer lowercase f. But it's denoted by n mu, or mu n, doesn't really make a difference. N is the normal force, and we know that the normal force is equal to mg. For now, next week that will change. I'll just introduce it now. It's actually equal to mg cos theta, and we'll see what we mean. But mu is the coefficient of friction. And all the coefficient of friction is that it's a measure of the degree of roughness of the object, or between the object and plane. And because there's two types of friction, I can have Fs and Fk, static friction and kinetic friction, and these are going to be equal to mu s n and mu k n, where mu s and mu k would have their own respective value. Now, you'll never have to remember what mu s and mu k are for different surfaces. There's no point. They'll either give it to you or you have to solve it. There's no constants that you have to remember. Oh, yes, I forgot this was here. For some reason in this module, if we go back, it wants us to analyze the acceleration of a single object subjected to a constant net force and relate the motion of the object to Newton's second law through blah, blah, blah. Graphs, vectors, quantitative descriptions. But one thing that textbooks like to explain is that, remember when we derived the Suvat equations for module 1, where we had accelerations equal to delta v on delta t, so that's how we get v equals u plus at, and then other things to get s equals ut plus half at squared, etc., etc. Now we can actually derive these other equations through looking at a velocity time graph. So let's say that I have an object and that object is experiencing a force. Now we know through velocity time graphs that the gradient of a velocity time graph is the acceleration, and the acceleration times the mass is the force. So here we have a positive gradient, and that's going to result in a positive acceleration and a positive force. We can actually derive the Suvat equations through this method. The first one is, let's calculate the area through this rectangle plus this triangle. Now, the area of a velocity time graph is just a displacement. So what's the area of this rectangle? So S is just going to equal to ut plus half base times height for this triangle. And half times base, the base is, as we can see, t, times height. And the height, as we can see, is going to be v minus u. But we know that acceleration is equal to v minus u on t, which is just delta v on delta t. So if I rearrange for v minus u, that's just going to equal at. So if I sub that in, I'm just going to get s is equal to ut plus half at squared. And that's how you can derive the first equation, s equals ut plus half at squared. The last formula is obviously v squared equals u squared plus 2as. But how do we actually get that? I've already calculated the area. The trick is we can calculate the area through assuming that this is a different shape. This is technically a trapezium. I have two parallel sides and, well, trapezium. So once again, we're going to have S, and the area of a trapezium is h on 2 a plus b. The height of the trapezium is obviously t, because this is technically like this. So t on 2, a plus b. And we can see that a is obviously going to be u. And we can see that v is obviously, b is obviously going to be v. Because, well, in a trapezium, a and b are just the lengths of the opposite of the parallel sides, and h is the distance between them, or the length between them. Once again, using this equation here, we're going to have a is equal to v minus u on t. So let's get rid of that pesky t. So we're going to have T is equal to V minus U on A. And if we sub that in, we're going to have S is equal to V minus U on A, 2A, because it's just going to be 2 times A, I hope we can see that, times U plus V, which is just going to be, if we take out the 2A, S is going to equal to 1 on 2A, V minus U, V plus U. I just swapped around the U and the V because obviously you can add them. And we know that this is a difference of 2 squares. And if I multiply the 2A over, I'm going to have 2AS is equal to V squared minus U squared. And that's how we get V squared is equal to U squared plus 2AS. So that's other ways that we can derive the equations of motion graphically through, well, this. If you have any questions about this, by all means, please ask me in class. Okay, so we have another concept check. I'll pause for 30 seconds, and then I'm going to resume the booklet. Okay, so question 1 is just describing, just qualitatively applying Newton's laws. Question 2 I already did. I kind of forgot that was there. Do not do question 3. We obviously have not done question 3. This accidentally snuck in earlier. And same with question 4. So just do question 1 and 2 for this concept check. Okay, so we're kind of finished with friction, not really, because obviously we're going to look at it next lesson in a different context, but just note that friction is a resistive force that points in the opposite direction to the direction of motion. And friction is equal to mu n, where n is the normal force and mu is the coefficient of friction, which is a measure of the roughness of the surface between an object and the surface. Also note there's 2 types of friction, static friction and dynamic friction. Static friction is where friction is the friction that must be overcome for an object to not be stationary, and then dynamic friction is the friction that opposes an object when it's moving. Now let's talk about tension. What is tension? Well, let's kind of, I'll hide that diagram for now, even though you've probably already gone ahead. But let's say I have a box, and this box is connected to a string that is suspended from the ceiling. Is this box moving? No, it's not. But if we look at the forces on the box, we can obviously see that I'm going to have my weight force pointing down. But just like in the case where if I'm standing up straight, there must be a normal force that counteracts the force of gravity, there must be a force that counteracts the weight force of the box here. But this box isn't touching the ground, so what kind of gives? And that is because the force is actually the tension force. And what the tension force is that it is the force that a string exerts on a mass. So I'll just pause for a second to let that sink in. But the reason why the tension force exists is because, well, if the object is stationary, there needs to be a force to counteract the weight force. And the way the normal force, the tension force works is that it always points away from the mass up the string. So it never points to the mass from the string, it points away from the mass up the string. And from this, we can see 3 main cases. And the 3 main cases are where if the box is stationary, if the box is falling down, and if the box is moving up. So in the first case where the box is staying still, well, if we look at our net force, so I have sigma F, that's going to be T minus mg. Now, sigma F, a way you can think about this is force up minus force down, force left minus force right, etc., etc. You just pick one direction and then subtract the other direction, because technically we're adding them. But here I have T minus mg, but the net force, if the object isn't moving, is 0. So hence, if T minus mg equals 0, T is equal to mg. Just like how if I'm stationary on the ground, N is equal to mg. As we can see that. The second case is if my object is falling. So in this case, I'm going to have sigma F is equal to T minus mg once again, but sigma F is equal to minus ma. And the reason why it's minus ma is because, well, mass doesn't have a negative value, but the acceleration is pointing down. And we always say that down is negative. So we're going to have T minus mg is equal to minus ma. And then we don't like having negatives on this side, so we're just going to times everything by minus 1. So we get mg minus T is equal to ma. And we can see here that if we wanted to rearrange for the tension, we'll get T is equal to m bracket g minus a. And then the third case is obviously going to be if acceleration is pointing up. And if acceleration is pointing up, I won't go through the math because hopefully you're able to see it by now, but just know that we get T minus mg is equal to ma, and we get T is equal to m bracket g plus a. So that's it for tension. So you should be able to do question 1, but I will do question 2. Are there any other questions I need to do? Okay, let's do question 2, and then let's do question 5. So you're looking at this going, what in the world is this? This is nothing even related to what I just spoke about on the previous page. Well, it actually is. This is called an Atwood machine, and an Atwood machine is just a pulley. And this is technically 2 separate cases of the cases, rather, I was just trying to avoid saying that we looked at earlier. So let's look at X. X is, well, firstly, we have to look at which one's heavier. Is X heavier or is Y heavier? Well, we can clearly see that Y is heavier, so X is going to be moving upwards. So if X is moving upwards, so this is going to be T, this is going to be mg, and this is going to be ma. So I'm going to have ma is going to equal to T minus mg. And similarly for Y, well, Y is traveling down. I'm just doing this quickly because it's a crash course. Obviously, if you want to revise the notes, they're on the previous page. And we're going to have ma is equal to mg minus T. Now, please know that these 2 masses are different. So I'm going to use capital M for Y because it's bigger. And so now we have to determine the net acceleration of the system of masses. How do I do that? I have 2 different equations. That's kind of the idea. In these questions, you're going to only be asked to find one of 2 things. You're either going to be asked to find the tension or the acceleration. We're actually asked to find the tension in the next question. Tension in the string. If you're asked to find the acceleration, you're going to perform a simultaneous equation by substituting through t. And if you're asked to find tension, you're going to use a simultaneous equation to substitute through A. We'll see what I mean. In this equation, I have MM. I'm asked to find A, and I know what G is. I don't know what T is, but I don't care for what T is. So I'm going to substitute through it. So for X, I'm going to do T is equal to MA plus MG. And I'm going to substitute this into equation Y. And that's going to result in MA is equal to MG minus MA minus MG. So I'm going to skip ahead here, but basically we're going to get A is equal to G M minus M over M plus M. I'll just give you a second to figure out how I did that whilst I just plug in the numbers on my calculator. And this is 4 meters per second squared. All right. Now, question B asks for the magnitude of the tension in the string, but I said earlier that if we're asked to find tension, we're going to substitute through A, but there's a catch. We're going to only substitute through A to get tension if we're asked to find tension first. If we're asked to find the acceleration first, well, look at this question. Look at this equation here. T is equal to MA plus MG. I know what G is, I know what little m is, and I know what A is. I just found A. And that is going to be my tension. So T is just MA plus G, which is going to be 138 newtons. Because we've already kind of done the heavy lifting. When we rearranged for T to sub it in, we created an equation for T. So we can use that same equation to substitute for T. Question 4 is very similar. Okay, so question 5, and I really recommend that you do question 5. I'll take 10 seconds in case you want to do it on your own. Question 5 is an interesting question because it involves a lot of things that we've covered. So if I have a box, right, and this box is falling with an increasing speed, so it has a force downwards MA, T, mg. So straight away we can see that sigma F is equal to minus MA, which is going to be equal to T minus mg. We're asked to find what tension is, so I'm just going to rearrange. So I'm going to have T is equal to mg minus A. You can see the above equations if you want to know how I got that. I know what M is. I know what G is. I need to know what A is. What are the equations that can give me A? Initially at rest, okay, U equals 0. 22 meters in 5 seconds. S is equal to 22 and T is equal to 5. And obviously A is equal to what we don't know. So by the toolbox method, we can see that I'm going to use S is equal to UT plus half AT squared. And I'm just rearranging for A. So for rearranging for A, you can do it, but I'm just going to jump to the answer. We're going to have A is equal to S minus UT times by 2 divided by T squared. Is that right? Yep. Oh, actually, yeah, that U is equal to 0. So it's just 2S on T squared. Yeah, that's interesting. So that's going to equal 1.76. So T is going to equal 5, 9.8 minus 1.76. Which is just 40.2 newtons. So we can see that we can answer questions in Module 2 using the tools that we developed in Module 1, which is very important to consider. Okay, so we're on Lesson 3 now, and Lesson 3 is inclined planes. So what is an inclined plane? Well, an inclined plane in a nutshell is just a plane that is not parallel to the floor. It's just any plane that is an angle between the floor and the actual surface. So an example would be like if you tilted your book at an angle. That's an example of an inclined plane. And it's very interesting the implications of an inclined plane because we have to consider the frame of reference of the box. From our perspective, it looks like the box is sliding down the slope or moving up the slope or moving up perpendicular to the slope or moving down perpendicular to the slope. But remember, from the box's perspective, it's actually traveling forward, backward, up or down, etc., etc. And what we can do is we can kind of resolve the forces that are occurring in the box's frame of reference in our frame of reference. So for a box that's sliding down a slope, this is just a model diagram. We know that gravity acts straight down, and we can resolve this into mg cos theta, mg sine theta. And well, very interesting. Normal. Why isn't the normal force straight up? Why is the normal force off at an angle? Well, that's because the true definition of the normal is that it acts perpendicular to a surface. If this was my slope, the normal force would be here. If I was on the ceiling, technically my normal force would point downwards, the same as gravity. It's just a weird implication, but it's just, remember, the normal force is the reaction force that the ground exerts based on you kind of being there. So here we have the normal force and we have mg cos theta. So because they're the only two forces pointing upwards and downwards, we can assume that the normal force is mg cos theta. I hope we all remember that identity. And then obviously force pointing down the slope, we have mg sine theta, and then we have friction pointing up the slope, etc., etc. So I'll go through some examples. I really hope that you're familiar with these questions, but I'll just do 3 or 4 just to build up the strength. So a block of mass m is sliding down a 45-degree frictionless incline. Take g equals 9.8. Find the acceleration of the block down the incline. Well, the first thing I do with these questions is I always draw a diagram because you never know what you're going to get. So this is 45. This is the block. This is mg. This is mg cos theta. This is mg sine theta. The normal force is obviously going to point directly upwards. So that's going to be N. And, well, let's do 2 things. The first thing that we're going to do is the net force perpendicular. Is the box flying up off the slope or sinking down into the slope? No, it's not. So this is going to equal to 0. So this is going to be equal to n minus mg cos theta, because force this way minus force this way. So hence we're going to have n is equal to mg cos theta. And then secondly, we're going to have force parallel to the slope, because this force is parallel to the slope. And that's just going to equal to force down minus force up, or force up minus force down, whatever you pick. I'm personally picking force down minus force up, so I don't get a negative. And that's going to be mg sine theta minus 0. So that means that the net force down the slope is going to be mg sine theta. It's asking for the net acceleration. So the net acceleration down the slope is just going to be g sine theta. And I hope we can see how that works. I do recommend that you have attempted these questions or looked at some information or even read through the notes before you attempt these questions. You can get away with not reading some of the notes, but you really have to read these notes. It takes a while to wrap your head around inclined planes because there's the whole frame of reference and just it's very math heavy, but I can assure you that once you do 20 questions, you'll be fine and everything will work out. Okay, question 4. A particle of mass 5 kilos rests on a 30-degree inclined plane. So this is obviously going to be my inclined plane, 30 degrees. mg sine theta, pointing down, mg cos theta, obviously the normal force. And we're told that a force F of magnitude 30 newtons acts on the particle in the direction parallel and up the inclined plane. And so this is lowercase f. Question B, asks for the force of friction acting on the particle. Now it says that the particle of mass rests, which obviously is going to imply that it's, well, at rest. So in order for it to be at rest, this means that all the forces have to cancel, which means that there must be 30 newtons pointing down the slope, which must means that the friction must be 30 newtons down the slope. I hope that isn't too hard to see. These forces must cancel out for the object to have no force and hence be stationary. And then find the normal force exerted by the inclined plane on the particle. Well, once again, we can clearly see that by doing, well, I'll do this one first. That's going to equal to force applied minus F, which is 30 minus 30, which is 0. Hence, box has no acceleration and is stationary. I hope we can all see that. I know I kind of jumped a little bit. But once again, if we do sigma F perpendicular, that's going to be to this force minus this force because it's just the perpendicular forces. There's only two. There's normal and mg cos theta. So n minus mg cos theta. I'm not accelerating up or down, so this is equal to 0. So we can see that n is equal to mg cos theta, and then just sub in whatever it is. Know that theta is 30. Yeah, this angle and this angle are the exact same. All right, so for question 6, Determine the acceleration of the block below if the coefficient of static friction is 0.343. That's actually a trick question. If it's static, is the box moving or stationary? Stationary. So if it's stationary, it would be 0. But that's just probably a poor question on my part. So we'll change it to kinetic friction. So once again, we'll draw all of our forces. So mg cos theta, mg sine theta, n. And it doesn't say much, but we'll just assume that the box is sliding down the slope. So V's down the slope, and we have F up the slope. So remember, once again, we're going to have sigma F perpendicular. And I think we can all see by now that this is going to be n minus mg cos theta, which is equal to 0. So we can just clearly say that n is equal to mg cos theta. I hope we can all see that now. And well, the second thing is actually a little bit different. So we have sigma F, and that is, remember, force down the slope minus force up the slope. That's going to equal to, oh no, it's going to equal to mg sine theta, because down the slope, minus the force up the slope, which is obviously the friction force, because the friction force points in the opposite direction. All good so far? And this is obviously going to equal to ma. So if it asks for the acceleration, well, a is just going to equal to mg sine theta what is happening? There we go. Mg sine theta minus F on M. But hang on, we don't know what the friction force is. Well, we actually do. Remember, the friction, I don't know what's happening. Friction is technically equal to mu n. And well, we're told kinetic friction, so it's just going to be mu k fk n. So that's going to be mu k n, but we don't know what the normal force is. Oh, but hang on, we actually do. We just showed that n is equal to mg cos theta. So we're actually going to sub that into this equation. So we're going to have A is equal to mg sine theta minus mu k mg cos theta on m. All the m's are going to cancel. So I'm just left with the acceleration down the slope is equal to g sine theta minus mu k g cos theta. You may be kind of freaking out, going like, oh my gosh, there's like so many different cases. What am I going to do? I actually highly recommend not memorizing every case, because it can become very tedious and it's just no reason. What I just do is just follow very simple steps that lead to a generalization for every idea, every type of question. The first step is to draw a diagram. The second step is to calculate sigma f perpendicular and sigma f parallel. Remember, sigma f perpendicular is just force up minus force down, and then sigma perpendicular is just force down the slope minus force up the slope, or force up the slope minus force down the slope, you choose. And then you're just going to kind of, well, I think it's very logical how this question worked. I have that mu f perpendicular is equal to force down minus force up the slope, which is mg sine theta minus f. And I'm moving, so this has to be equal to a number. Must find the acceleration. So the acceleration is going to equal to mg sine theta minus friction on m. What is friction? well, I don't have a number, so it has to equal mu n. Okay, I have what mu is, it's given to me in the question, but I don't have what n is equal to. Oh, but hang on, by doing mu perpendicular, I can get n is equal to mg cos theta. I sub that in, and now I'm done. So basically, physics in a nutshell is just applying your steps. So drawing a diagram, so step 1, step 2, step 3, and then answering the question, but every time you hit a roadblock, you use something you acquired in the previous steps to move forward. So we can see here, I don't know what f is. That's a roadblock, but f is equal to mu n. But I don't know what n is equal to. Oh, but n is equal to mg cos theta. And so you kind of avoid those roadblocks by having a good starting platform that hopefully you can use for all questions. Okay, I'm going to do question 10, and then question 12, I'm going to leave that because that's a really, really good question. It involves everything. But question 10 involves inclined plane questions with tension. So if I aim to do my free body diagram, well, what actually happens? Well, I'm going to have mg sine theta, mg cos theta, n, and well, it says here a box of mass 10 kilograms rests on a 35-degree inclined plane with the horizontal. A string is used to keep the box in equilibrium. So that means that there's no force traveling down the slope, like from the box. The velocity is 0. It's in equilibrium. Or the acceleration is 0, rather. Part B asks to find the magnitude of the tension in the string. Well, this is a very interesting question because we get presented with many different kind of things, right? So let's do sigma F parallel. That is going to be force down the slope minus force up the slope. So as always, it's going to be mg sine theta minus, well, it's very interesting. What is the force acting up the slope? I said it was tension, but this tension is at an angle. And that is where people don't really understand physics. And these are the steps that will help you secure a band 6 and completely dominate the top of your class. This T is offset by an angle, but it's still technically a force because it's a vector. So we can resolve that tension vector into T cos, I won't use theta, I'll use alpha. It's a different degree, and T sine alpha. So we can clearly see here that parallel is equal to mg sine theta minus T cos alpha, and this is actually equal to 0 because I'm not moving. So to find T from this, and just very quickly, I will do perpendicular because I always say to do 1, 2, and 3, but this is a little bit different. So once again, I'm going to have n minus mg sine theta, but is that the only force pointing upwards or downwards? No, actually. I also have T sine theta pointing up. So I'm actually going to have n minus mg sine theta plus T sine alpha is equal to 0. So that's why I said n is not always equal to mg cos theta. It can also be, it's just dependent on what forces are perpendicular to this plane. But anyway, to rearrange for T, we can clearly see that we're going to use the first equation. And just rearranging, I'm just going to have T is equal to mg sine theta on cos alpha, and whatever that's equal to. That is equal to 62 degrees. Oh, 62 Newton, sorry, not degrees. And then part B asks for the magnitude of the force of friction acting on the particle. Well, that's very interesting because, well, let's think about this. There is no friction because it's stationary. Is there a way we could get around to friction? No. So I think that's just a botched question, because the force of friction, assuming that this is kinetic friction, it would obviously be 0. Because static friction, we don't have a mu to deal with. And I kind of stuffed up. This should be cos theta. Anyway, so I'll give you another 30 seconds or so to figure out the rest of these questions, by all means. Okay, I'm back. So we're going to start the next lesson, and the next lesson is all to do with work, energy, and momentum. So firstly, let's talk about energy. What is energy? Well, there's many different types of energy, as we know. We have kinetic energy, potential energy, heat energy, electrical energy, chemical energy, so on and so forth. But the overarching definition of energy is that it's a scalar quantity that can be defined as the capacity to cause change. So what that means is that all energy can cause change. There are two main types of energy. We have kinetic energy and potential energy. But before we can look at energy, we must look at what a system is. A system can be defined as the entire observation. For example, we have an open system. An open system is a system that exchanges both matter and energy with its surroundings. A closed system is a system that only exchanges energy with its surroundings. And an isolated system is a system that does not exchange matter or energy with its surroundings. So what would be an open system? Well, an open system would be pouring water into a kettle and then boiling that water. Because I introduced matter, I put water into the kettle, and I introduce energy by boiling the kettle. A closed system would be I don't know, something like boiling a soup or cooking a soup. You're not putting anything more into the soup, but you're heating it up by introducing heat. And then lastly, an isolated system, or an example of an isolated system would be, I can't put energy in or I can't put matter in. It's very hard to have an isolated energy in reality, although we always assume that we have an isolated energy in physics, isolated system in physics. I keep saying isolated energy, I apologize, isolated system. An example of an isolated system would be if I throw a ball in outer space. If I throw a ball in outer space, the mass is not changing, and the energy of the ball, whether it be kinetic energy, potential energy, etc., is also not changing. Because the ball's going to stay the same speed because it's not under any force. Because gravity is incredibly weak in outer space. Some characteristics of energy include energy can take on many different forms, such as light, sound, nuclear, etc. And energy can either be created or destroyed, although it may be transformed from one form into another. That is the law of conservation of energy. It's very important. And what this means is that the total energy, which is called the mechanical energy, so the mechanical energy is going to be equal to the kinetic plus potential, is always going to be alpha, which is just a number. So what that means is that if I drop a ball, I'll use this example later. All right, what is work? Well, when a net force applied to an object has moved that object a certain distance, we say that work has been done on that object. Work is denoted through the formula work is equal to Fs, or if we're looking in 2 dimensions, W is equal to Fs cos theta. Very straightforward. The units for work is in joules. And well, that's very interesting because we have work that's in joules and we have energy that's in joules. So from this, we get the work energy theorem, which states that the work done on the objects is equal to a change in energy of the body. And we're going to see what a change in energy means. So we have work is equal to delta E, change in energy. Kinetic energy. Kinetic energy is just the energy of a moving body. Kinetic energy is equal to half mv squared. Since work done is defined as a change of energy, we can say that work is equal to delta kinetic energy, which is equal to the kinetic energy final minus the kinetic energy initial, which is equal to half mv squared minus half mu squared, where u is obviously the initial velocity. And as we can see, we can factorize everything out. The other type of energy is potential energy, and it's called potential energy because it has the potential to do work, whereas kinetic energy is causing work, because if I have a velocity, that means that I am traveling a distance. So W equals Fs cos theta. All right, I'll give you guys about 30 seconds to do this question before we move on. All right. I do apologize if that may have been a little bit quick, but that's because work and energy, there isn't really much to it. So we know we can define them. We know that the 2 different types of energy are potential and kinetic. Calculate the work done by a pram that's being pushed 5 meters with a force of 22 newtons with an angled elevation to the ground of 30 degrees. Well, that's just W is equal to Fs cos theta. But where the real questions start to come in is things such as question 4. So a 2-ton truck, so that's 2,000 kilograms, is traveling at 100 kilometers per hour and slows to 60 kilometers per hour as it leaves the freeway. Calculate the work done by the truck to slow down. Well, typically work is equal to Fs cos theta. But that doesn't work, even though we can assume that theta is equal to 0 because there's no triangle formed. I don't have a force and I don't have a displacement. But remember, work is equal to a change in energy. And the change in energy that we're looking at is the change in kinetic energy, which is equal to half m v squared minus u squared, which is going to equal to half m. Remember, you must convert kilometers per hour into meters per second. So we're going to have 27.8 squared minus 16.7 squared. And then whatever that is equivalent to would be the answer. Then for part B, we can see that, well, we have our work, Fs cos theta. As in, we have our number in the previous question. I'll just calculate it. About 50,000 joules. By the toolbox method, we have S, and we asked to find what F is. And we can assume that theta is equal to 0 because, well, there's no triangle being formed because we're not given an angle. And we know that work is approximately equal to 50,000 joules. So we can just do work is equal to Fs cos theta, where this is obviously 1. So we're just going to have F is equal to work on S, which is approximate, I don't know what's happening. Sorry about the technical difficulties, which is about 330 newtons. And then from that, we could calculate the acceleration of the truck, the time that the acceleration takes place, etc., etc. There's really, yeah, it's endless what we could do with this information. And then question 5, calculate the work done on a 1,000 kilogram car if it travels at a constant speed of 22 meters per second for 10 minutes. Well, two ways we could do this. We could do work is equal delta kinetic energy. Does my kinetic energy change? No, it's constant at 22 meters per second. So therefore my work done is going to be 0. What about Fs cos theta? Well, I do have S. I could calculate S through velocity times time, but do I have a force? What's my force? Well, do I have an acceleration? Once again, my velocity is constant, so I can't have an acceleration. And see, you're back at square one where the work done is just 0. Okay, gravitational potential energy. So the primary potential energy that we look at within this module is gravitational potential energy. And what is it? Well, it's the amount of energy available to an object due to its position within a gravitational field. And very similarly, where work was equal to a change in kinetic energy, work can be equal to a change in gravitational potential energy. And the gravitational potential energy is given as U is equal to mgh, where h is the height above the ground. And as we can see, we have our work expression for delta U, mg hf minus hi. And well, once again, we can see how these are actually linked. So say we have v squared is equal to u squared plus 2as, just a normal velocity equation. Well, if you drop an object, u is going to equal to 0 and a is going to equal to g. So we're going to have v squared is actually equal to 2gh. But if we plug this into the kinetic energy formula, we're going to have half mv squared, but v squared is 2gh. So it's going to be half m 2gh, which is just mgh. So we can see that the kinetic energy gained by the object falling to the ground is going to be equal to the potential energy the object has lost by falling to the ground. Because remember, h is how far the object falls. So it's saying that the initial potential energy is equal to the final kinetic energy. And that's very important when we start to do questions. Okay, I'll give you guys 30 seconds and then we'll reconvene. Okay, we're back. Calculate the kinetic energy of the car for question 1, just plugging into the formula. Determine the change of kinetic energy of the brick, just plug into the formula. Determine the kinetic energy of a space probe, just plug it into the formula, but please note, convert kilometers per second into meters per second. Question 4 is the type of question that I want to talk about. Question 4 combines a lot of interesting things that we've covered, but not explicitly connected. So let's talk about this very quickly. A mass of 5 kilograms is dropped from a height of 7 meters and falls to the ground below. Let's find the potential energy. mgh, which is going to equal to 5 times 9.8 times 7, which is equal to 343 joules. Let's calculate the greatest kinetic energy that the mass can gain by falling. Well, logically, the mass is going to be the fastest just above where it hits the ground. So we know that kinetic energy is equal to half mv squared, but let's calculate v squared, because obviously we don't know what v squared is. We can do it through well, just looking at this. So it says that the mass is dropped and we know what S is. So U is equal to 0, S is equal to -7, and we have G is equal to -9.8, and well, we're trying to find V. I think we can see that we're going to be using V squared is equal to U squared plus 2AS. So we're going to have V squared is equal to 2AS because obviously U squared equals 0. So we're going to have half times M times 2AS. Let's just plug everything in, shall we? So we're going to have half times 5 times 2 times 9.8 times 7, sorry. Look at that. It's 343 joules. But that's really interesting. And why is that interesting? Well, consider this. If I drop the ball at this point, we know that the mechanical energy is equal to U plus K. And same here. At this point, when I've dropped it, U is equal to 0. So this is just equal to U plus 0, which is equal to 343 joules. At this point, we can assume that U is equal to 0 because I'm just above the ground, like I'm a micrometer, a picometer, a femtometer above the ground. I'm so small off the ground it barely counts. So this is going to equal to 0 plus K, which is equal to 343 joules. But what does that mean? Well, that means that at any point in the ball's flight, the kinetic energy and the potential energy are going to add to 343 joules. We'll do an example. Let's calculate the energy of the ball at h equals 5. So I'll just section this off. So if h is equal to 5, that means that U is going to equal to mgh. So 5 times 9.8 times 5, that's going to equal to 245 joules. K is going to equal to, well, we can see here, that's going to equal to half m to as. Remember, s is how much the ball has fallen. If h is equal to 5, s is going to equal 7 minus h. So s is just going to equal to 2. So if I plug everything in, so half times mass, which is 5, times 2 times acceleration, which is 9.8, times height times distance fallen, which is 2, I'm going to get 98. And U plus K is equal to 245 plus 98. Which is equal to 343 joules, which is pretty cool in my opinion. It's just stating that at every point, the kinetic and potential energy add to 343 joules, no matter what. And then question 5 is a good question. Don't overthink question 5. Okay, let's talk about power. So we know what work is. Work is the change of energy, or Fs cos theta. But we can also have something called power. And what is power? Power is the work done over a certain time, or is equivalent to the change in energy over time. The units for power are joules per second, because this is joules divided by second, so that's going to work as joules per second. But a joule per second is actually equal to a watt, W-A-T-T. Also, we know that W is equal to Fs cos theta. So we're going to have P is equal to Fs cos theta on T. Well, that's very interesting. Let's take out the F and cos theta. S on T, well, S on T is just average velocity, because the reason why it's not instantaneous velocity is because Usain Bolt can run 100 meters in 10 seconds, but his speed at the end of the race is not equal to the speed at the start of the race. So hence we're going to have FV average cos theta. So what is the relationship between work and power? So we can clearly see here that, well, work is a measure of the change of energy, but power is a measure of the change in energy over time. So an example will be a person walking up a flight of stairs compared to a person running up a flight of stairs. They both do the same work because they're both moving up the same height. They still have the same delta H. But the runner will feel more tired because they used up more energy in a shorter period of time. Hence, the runner is applying more power than the walker to go up the stairs. Once again, I really wish we could do this in person because I could ask questions, and if anyone had any questions, they could ask. But yeah, I'm just going to wait 30 seconds, just go through the questions, and then we'll reconvene. Okay, question 1 shouldn't be too bad. It's just a formula. Question 2 shouldn't be bad either. Question 3 is good, and question 4, yeah. All these questions is very easy, just using the information that we can see on this page. Okay, momentum. So we're on the home stretch, so all we have to do is talk about momentum, impulse, and then that's it. That's the entire module, which is pretty cool. So what is momentum? So one of the things that physicists were thinking about is, what is the importance of the relationship between mass and velocity? Well, you might be thinking, well, how is there a relationship between mass and velocity? Like, we know that there's a relationship between mass and acceleration. How could there be a mass between an instantaneous velocity and a mass? But the idea is that an 80 kilogram man, as these are just examples, but I hope you'll see the principle after I talk about these examples. An 80 kilogram man running at 5 meters per second is a lot harder to stop than a 30 kilogram 6-year-old running at the same speed. Also, a bullet fired from a rifle with a velocity of 1500 meters per second will do a lot more damage than an identical bullet thrown at the target by hand. So the point that I'm trying to get is that an object's mass and velocity can really affect how difficult it is to stop. And the measure of this is the momentum. And the momentum is mathematically defined as mass times velocity. And as such, the units for momentum are kilogram meters per second. Also, since momentum is a vector quantity, its direction will be in the same direction as the velocity. And because because momentum is a vector, we can treat it and we can find the resultant and sum it and things like that we'll be doing in module 1 and with forces earlier in this lesson. There's a very interesting relationship between momentum and force, and we're going to talk about it next lesson. But the idea is that F is equal to ma, A is equal to V minus U on T. But technically, a change in momentum is going to be equal to the mass times delta V, which is just the final velocity minus the initial velocity. So hence, force is actually equal to ma, which is actually equal to the change in momentum over time. And the change in momentum is something called impulse that we'll probably get to in about 10 minutes or so. But I digress. The most common questions regarding momentum that you will see in this module are conservation of momentum questions. And what are conservation of momentum questions? Well, they're essentially questions where if, say, object A collides with object B, what would be the velocity of object B after the collision? And we can very easily calculate this. Just like the law of conservation of energy, the law of conservation of momentum is just a universal law that states that momentum is always conserved in a collision if there are no external forces acting on the system. So an external force would be friction. So we just basically assume that there's no friction in this example. It's given by the formula sigma pi is equal to sigma pf, which just means that the sum of all momentums before is equal to sum of all momentums after. And for a two-body system where I have A and B, that's just going to equal to ma ua plus mb ub is equal to ma va plus mb vb. And of course, you'll just rearrange for the quantity that we need, substitute, and we're done. So these questions are concerned with collisions, and there's a main type of collision that we like to talk about. So a collision is defined as a brief, usually strong interaction between usually two objects where momentum is conserved if there's no external forces acting on the system. There are two types of collisions: elastic collisions and inelastic collisions. An elastic collision is, as we can see, if kinetic energy is conserved in the collision and this property holds. And as you can see, you can very easily derive a formula similar to this formula above using this series here. And then obviously a inelastic collision is going to be when these aren't equal, so energy is lost. And in the real world, there are actually no real examples of elastic collisions because every collision involves some energy transformation. So for example, if two cars crash, well, some of that energy is converted into sound energy because we can hear the collision. Some of that energy is going to be converted into heat energy because when they crash, they might rub against each other and that rubbing forms heat due to friction. Things like that. Okay, I'll give you guys about 30 seconds, so just pause it here and then we'll reconvene. Okay, I'm back, but before we go any further, I just want to do an audio check, so just give me a second. Hello. I'm just listening to myself on the other computer. Alright, looks like we're good. Okay, I'm actually back down. So question 1, P equals mv, but please include the direction. Momentum is a vector, and as such, you have to include the direction. So we have P is equal to 60 times 9.7. That's going to equal to 582 kilogram meters per second north. Question 2, once again, just convert kilometers per hour into meters per second. Question 3, easy. Question 4 is the typical type of questions that we expect to see. Sorry, I'm just looking at any other questions. Yeah, they're all very, the rest of the questions are just collision questions. If you were stuck on question 5, coalesce just means stick together. So they become one mass. So here we can see I have MAUA plus MBUB is equal to MAVA plus MBVB. We also find the velocity of B after the collision. Don't worry, I'm not going to worry about the total kinetic energy of this system because that's just half mv squared A plus half mv squared B, so I'm not going to worry about it. But we're just rearranging for VB, and that's going to equal to MAUA plus MBUB minus MAVA divided by MB. Now let's sub everything in. A is 8 grams, so that's going to be 0.008 because we have to keep everything in kilograms. velocity 0.5 meters per second to the right. So I'm just going to do times 0.5 plus 0.005 for the mass of B times minus 1.2. Now, the reason why I do minus 1.2 is because it's to the left. It's the opposite direction. So because it's to the opposite direction, I have to include a negative because we're dealing with velocities. P is equal to mv, velocity. Now, we also know that the velocity of A after the collision is 0.1 to the right. So we do positive and everyone's happy. And then we divide that by mb. Putting everything together, we get VB is moving minus 0.24 meters per second minus 1, or just 0.24 meters per second to the left. And that is it. All right, so we'll move on to the next question. I'm just trying to copy this across. So for the next question, it says they coalesce. Now, coalesce just means stick together, and we're going to use essentially the same formula. But when something coalesces, VA is actually equal to VB. It just means that when they smash, like, so this car and this car, they smash to make a big car. Like they stuck together. Like you need a fire to separate them using all their fancy equipment. So what this just means is that we're going to have V MA plus MB. So V is actually equal to MA UA plus MB UB on MA plus MB. And MA is going to be 2000. MB is going to be 25. And very interesting, actually. It says that it collides with a small stationary car of 1,000 kilograms. So because it's stationary, UB is actually equal to 0. So that means that, well, it's 2,000 times 25 plus 1,000 times 0 over 2,000 plus 3,000. No, sorry, my bad. And so we get the final velocity is going to be 16.7 meters per second, or 16 kilometers, or 60 kilometers per hour, rather. So what it's saying is that, like, it collects the car. So this car is traveling this way, this car is stationary, and then as such, they have climbed together like that. But momentum must be conserved, so it's frictionless, and so on and so forth. Question 6 is similar. Question 7 is similar. And question 8 is similar again. So I'm being genuinely serious. These are literally the types of questions that you can expect to see when you are in an exam. And I'm just covering all the different types of questions. And, well, we'll do like a little recap at the end to talk about which questions are the hardest, which questions you should look out for, etc., etc. All right, we're on the real home stretch. So the final thing that we're going to talk about is impulse. And what is impulse? Well, impulse as a nutshell is just the change in momentum. So remember, delta P is equal to M delta V, because my mass can't change, but my velocity can. M delta V is equal to V minus U. And this is equal to impulse, which is denoted by I. Note that I has the same units as momentum because it is technically momentum, and it's in kilograms meters per second. And we get this very interesting equivalence out. So m's equal to ma, but ma is actually equal to delta v divided by t. Delta p divided by t, rather. And so we get two formulas. We get I is equal to mv minus u, and we get I is equal to f delta t. So that means that we can have a further equation that is going to be m delta t. And essentially we're just going to pick from equation 1, 2, or combine them in equation 3 to solve our questions. Generally in collisions, impulse is the same, because let's think about it. It's on the next page. Yeah, it is on the next page. But just to lead into what's on the next page, when I crash, right, so say I'm going 20 meters per second, my impulse is always going to be the same, right? Because my impulse through equation 2, I, is just going to be, I don't know, let's say a car's 1,000 grams. My final velocity is 0, and my initial velocity is u, which is 20 meters per second. So this is going to mean that my impulse is minus 20,000 kilograms meters per second. Okay, but this I is technically equal to f delta t. And that f delta t can mean, well, two things. Well, remember, my impulse isn't changing, which means that my f is inversely proportional to my delta t, because my f isn't changing. Remember, we've spoken about this. So if my f isn't changing, because my I isn't changing, then f is proportional to 1 on delta t. So that means that if I have a high delta t, I have a low f. And if I have a high f, I have a low delta t. And we can see this on the next page. So the process of minimizing an impact force can be approached from the definition of impulse. If an impact stops a moving object, then the change in momentum for that object is a fixed quantity, because it's obviously mass times the change in velocity. Extending the time of the collision will decrease the time average of the impact force by the same factor, which basically means that if I can increase the time it takes for the collision to occur, the less force is going to be experienced for the same impulse. And these are this is how safety features in cars work. So we have an airbag in the car, for example. So it's designed to inflate during an accident, and it's designed to increase the time it takes you to reach 0 speed, because it's like a pillow. It's like a big airbag. So because the time taken for you to reach 0, the airbag is going to reduce the force applied to the driver, because we have F is proportional to 1 on delta t. Another example is in baseball. So you'll notice that in baseball or softball or any of those sports, when they catch the ball, they always move their hand in the direction of the ball to catch it. They never, so if the ball is moving this way, they always move their hand away from the ball when they're catching it. And that's because, well, if you move your hand in the direction of the ball, this is going to increase the time it takes for the ball to come to rest in the hands. And by F is proportional to 1 on delta t, that's going to reduce the force on the hand. Okay. One of the last things, and I may have to go grab a charger soon, is looking at impulse and graphs. So in a nutshell, the impulse is just the area under a force time graph. So we can see here, the area under the graph is a triangle. So half base times height, that gives you the impulse of this graph. Last thing that we have to look at is impulse in 2 dimensions. So everyone didn't like relative velocity last module. Impulse in 2 dimensions is basically relative velocity, but with an added twist. Everyone is cheering right now. All right. So let's kind of do this. So these are the typical questions that you're going to get. So we know that I is going to equal to mv minus u. So let's consider this. Let's consider a dog running at 3.5 meters per second south, then turns east and runs at 2 meters per second. Calculate the impulse. Well, straight away, this can be u and this can be v. V minus u. So it's going to be 2 east. And what is the negative of south? North. So it's going to be 3.5 north. And luckily, in this example, I have given you a right-angled triangle. So by Pythagoras, we're going to have 2 squared plus 3.5 squared. It's going to be 4. We'll just do 4. And remember, this is delta V. And you must do theta. And calculating theta is going to be inverse tan 3.5 on 2, which is equal to east 60 degrees north, because remember we go east 60 degrees north. But remember, when I do Pythagoras, that Pythagoras is not the answer. That is only delta V. I must always multiply my delta V by m. So my I is actually 88 kilograms, direction of magnitude. 88 E 60 degrees north kilograms meters per second. And I hope we're familiar with this notation. Basically, it's because I'm looking east and then I have turned 60 degrees north, like that. Yeah, now I'm just being picky. So we can see that when we have to solve impulse in 2 dimensions, we must follow these steps. Add the 2 velocity vectors together, being mindful to add the negative of the initial velocity, draw the resultant. And this is because I is equal to m v minus u. If you're lucky and get a right-angled triangle, you can use Pythagoras to calculate the magnitude of the resultant. And the resultant is equal to delta V. Then you must multiply the magnitude of the resultant by the mass of the object to get the magnitude of the momentum. And then, if you're lucky, you can use right-angled trig or through the sine rule, calculate the angle and hence the direction of the momentum. And that's it. We are almost finished. We only have 2 concept checks to go, and we have officially finished module 2. I apologize if there's noise in the background. I am just getting my charger. Awesome. All right, so I'll give you guys about 30 seconds to do, just pause and do the questions that you want to do, and then obviously I'll go through the noteworthy ones. So here we go. All right, so I'm going to do question 1. One and 8. Yeah. Yeah. So question 1, because everything else is just pretty straightforward. Actually, no, I'm not going to do question 1 because question 1 is very easy. It's just south minus north. So, yep. Question 8 is a very good question, and it talks, and like I recommend that you revise angles on parallel lines before you do these types of questions, because you really do need to understand angles on parallel lines. So let's talk about this, right? So we need to calculate the impulse. The impulse is I is equal to m v minus u. This is v, so minus u is going to be this. So we're going to have 1.5, and then this is going to be delta v. And this is obviously going to be the angle is going to be theta, yeah. And this whole thing's going to be theta. All right, so let's talk about this. What in the world is going to be this angle right here? What is going to be that angle? It's very interesting. And the hint is parallel lines. Remember, these two lines are technically parallel. That's kind of your hint. I'll give you about 10 seconds. If you want to pause, by all means, but I'm going to reveal it after 10 seconds. Okay. If these two lines are parallel, that means that this angle and this angle are co-interior. What is this angle? Well, this angle is going to be 180 minus 30 minus 45, which is just going to be 105 degrees. And by definition, co-interior angles must add to 180. So that means that this is just going to be 75 degrees. And that's how we get it out. Very nifty in my opinion, but you must revise angles on parallel lines before we can do this. But then after this, all we're going to do is follow the steps. So what were the steps? Just to revise. Add the two velocity vectors together, being mindful to add the negative of the initial, draw the resultant, using Pythagoras or through the cosine rule. We don't have a right angle triangle, so we can't use Pythagoras, so we have to use the cosine rule. And that means that we need to use the sine rule to get the angle. Okay. What's the cosine rule? The cosine rule is c squared is equal to a squared plus b squared minus 2ab cos c, where for a triangle, this is c, this is angle c, this is a, and this is b. We have a and b. A is 1.5 and b is just 1. So, and remember, c is technically this. So we're going to have delta v, and that's going to equal to the square root of 1.5 squared plus 1 squared minus 2 times 1 times 1.5 times cos of the angle, which is 75 degrees. And that's going to be 1.57. But remember, impulse is equal to m delta v. So I is going to equal to the mass, and the mass of that is just 0.3. Just like that. And then also we need to calculate the angle. And the angle is given by the sine rule. And the sine rule is sine A on A is equal to sine B on B, which is equal to sine C on C. I'm just going to use sine A on A is equal to sine C on C. And that's because I said that A is 1.5 and we want to find this angle here. And we already know what the angle C is at 75 degrees. So that is going to mean that sine A is what I'm trying to find. So A is just going to be inverse sine A sine C on C, which is going to be equal to inverse sine. Well, A is 1.5. Sine 75 divided by C. C is not 0.47. C is the length of the side that we calculated, which is delta V, and that's 1.57. Which is 67 degrees. So what that actually means is, well, remember, this is just what alpha is equal to, because I said let this be alpha. Theta is the whole thing. Theta is alpha plus 45. So that means that theta is equal to 67 plus 45, which is equal to 112 degrees, which means that my drawing is wildly off scale. It should be something like, it should be something like here. Like that's where it should meet up. But I digress. This is kind of misfortunate. But because it's 112 degrees, that means that it's going to be 180 minus 112. So it's going to be 68 degrees above negative x-axis, and we are done. Because 112 plus 68 gives you 180. So it's just what 180 minus 112 will give you in this direction what it was actually equal to. So this is our answer. That and that. And obviously in the exam you'll have to structure your answer so it's more appropriate and like it's readable. But for the intents of a crash course where we've covered the entire module in probably about 3 hours, when it's all said and done, not too bad in my opinion. All right, last thing, so impulse and collisions. So we're going to be talking about impulse and collisions through Newton's third law. And what does it actually hold? So when A and B collide, through delta P is equal to F delta T, we can get the force of A on B is going to, so we have the change in momentum of A is going to equal to the force A on B times delta T. And then hence, we're going to have the change in momentum of B is going to equal to the force of B on A delta T, because it's a collision. The delta T is going to be the same, and well, we're going to see what happens. So remember, these two are equal through Newton's third law. FAB is equal to minus FBA. And we also have delta T's equal because they're part of the same collision. If you want more clarity, I suggest reading the notes. Yeah, it's just like they collide, and we're just talking about the collision in terms of momentum and forces. But hence, we can see that if delta T is equal for both, and FAB is equal to FBA, so that means that this side is technically equal to this side. So that means that the change in momentum of A must equal the minus of the change of momentum of B. But what does that mean? Well, all we're going to do is add this to this side, and we get the law of conservation of momentum, which essentially states that momentum always has to stay the same. The change in momentum of A plus a change of momentum of B must be 0. There's no momentum being lost from the system. No momentum's changing overall. So we can see that, thus using Newton's third law and our knowledge of impulse, we have shown that if there are no external forces, the total momentum of the system is not changed by the collision. Therefore, as we have said before, if we assume no external force acts during the collision, we can say that the total momentum of the system before collision equals the total momentum of the system after collision. External forces. So a lot of the things that we've been discussing regarding the law of conservation of momentum is how this only holds if there are no external forces. But, well, let's think about it. Aren't there external forces everywhere? Like when a golf club strikes a golf ball, surely there are external forces that act on the system of the ball and the club. And these two ones are pretty obvious. We have gravity and we have friction. Gravity must act on the ball, and friction must act on the club as it hits the ball. So what do? Well, we actually just neglect these forces. We just say that they just don't count. And they're negligible compared to the forces that we observe in the collision. And that's it. Final concept check before we reconvene. Once again, I probably didn't do this justice in the sense, like it's not super important, this section, but it is just to give you further information on why collisions, because like we've looked at collisions through momentum, and it's just referring to how collisions and Newton's third law intertwine, because Newton's third law is essentially a false description of what collisions are. But I digress. All right, I'll give you all 30 seconds. Feel free to pause the video. I'm just going to look through the questions to see if there's anything I need to do, and we'll reconvene soon. All right, so we'll just go through these questions. These are the last questions that we need to do, because after this it's just a prac and you can read through that if you wish. I don't really do pracs, unfortunately. So a student drops well, firstly we'll just do the shopping list, or the toolbox, whatever I call it these days. Calculate the impulse of the pool ball. All right. Give me 1 second. All right. Calculate the impulse of the pool ball. Now, what I was looking for in this question is, are there two ways that we can do this? Can we count this like through both equivalent ways? And the only way that I can really see this occurring is I is equal to m delta v, where that's going to be to 0.16. The final velocity is 0 because there's an instant of time before the ball's velocity is 0. And it claims that it takes 3.5 milliseconds. So minus 5.67. So it's going to And then I was also looking for the idea that we could like calculate F. Oh, that's part B. I was like, what am I doing with this? So yeah, okay, that makes so much sense. I genuinely opened up my solutions book because I've been winging like all the questions tonight, but I was just genuinely looking at my solutions book to see what it was. But anyway, calculate the average force, far out. So we know that I is going to equal to F delta T. So F is going to equal to I on delta T. And that's going to equal to 0.9072 divided by 3.5 times 10 to the minus 3. So that's going to equal to 259.2 newtons. And as we can see, this is just an application of the two formulas that we have seen earlier. Question 2, yep. Question 3, think about it. It's going to, by using crumple zones, it takes longer for the car to smash. That's your hint. Question 4, question 5, remember, it's just the impulse is just the area under the graph. So remember, we asked to find the final velocity. So we have force delta T is equal to mv minus u, where we know that u is equal to 10 and m is equal to 4. So F delta T, the impulse is just the force under this graph, and that's just a trapezium. That's just 5 on 2, 3 plus 5, and that's going to equal to 4 v minus 10, and then all we have to do is just rearrange. So we have v is equal to 15 meters per second. I hope that you can see this. It's just, we're asked to find velocity through force and time, and there's only one logical way that we can get to velocity through force and time, and that's through this equation here. The area under a force time graph is the impulse, so we just plug in and rearrange. That's all we're doing. And that's it. That's actually it. We have a prac here, but I don't really do pracs because I don't have the resources, unfortunately. But that's it. All we have left are these end of module questions. How many of them are there? There's 31 questions. They're all pretty good, pretty tricky at times, but they're all just meant to serve you and just kind of make you serve your understanding of this module. So in a nutshell, let's kind of go through the difficult things. So there are 2 or 3, or probably 4 difficult ideas in this module. The first one is absolutely inclined planes. You must perfect inclined planes. And there's many different ways that you could be asked inclined planes. You can be asked inclined planes without friction, inclined planes with friction, inclined planes with static friction, inclined plane with kinetic friction, inclined plane with a string, with tension. You get the idea. There's many different ways, and I don't recommend trying to memorize all of them because you'll just drive yourself crazy, but rather just employ the ideas. Net force perpendicular is force up minus force down. Net force parallel is force up the slope minus force down the slope, or force down the slope minus force up the slope. You pick. Draw a diagram, for the love of God. Please draw a diagram if you're going to, when you do incline plane questions. The second type of question is going to be these Pauli questions, these Atwood questions. Just refer earlier to what we spoke about. You must do the two cases, and then if you're asked to find A, substitute through T, find A, and sub it back into T. If you're asked to find what A is, if you're asked to find what T is, rearrange for A, substitute through A to get T, and then using your value of T, find what A is. It's just very easy simultaneous equation. One of the things that I really don't understand about physics is that a lot of students, they don't really understand the math behind it, but it's literally just math, but with different letters. Like people will see T is equal to MA plus MG, and they'll see these two equations, and G is equal to 9.8, and capital M is equal to 24, and lowercase m is equal to 10, and we know what we don't know what T is, but we don't know what A is, but we want to know what A is, but we don't care what T is. And people just freeze and they go, I don't understand. But you do understand, it's just math, and it's just doing a simultaneous equation. That's all you have to view it. It's just applied math. That is literally what physics is. It's just applied mathematics. The next hard thing is going to be these questions I spoke about, where I drop an object, and you must, a lot of people actually don't understand that it's 343, 343 throughout the entire flight. But I hope that I was able to show you that at this highest point it's 343, at this lowest point it's 343, and at some random spot in the middle at h equals 5 and s equals 2, it's also 343. So I hope that made a lot of sense. Momentum is it's not tricky. You just need to understand this formula, and you have to apply this formula to events, like how we can see here. I can get a little bit messy because you have 1, 2, 3, 4, 5, 6, 7 things to sub in. So it can get pretty messy and you can make a mistake, but just do questions and you become very familiar with the work. Impulse, very straightforward. The only thing that isn't straightforward are these impulse in 2 dimensions questions. So calculate the impulse when I have a change in velocity, but it's just v minus u. We have to basically do these steps. Add the 2 velocity vectors together, being mindful to add the negative of the initial velocity, draw the resultant, using Pythagoras' theorem if we get a right-angled triangle, or using the cosine rule if we don't. Calculate the magnitude of the resultant. This resultant is delta V. It's not the impulse. You have to multiply this resultant by the mass to get the magnitude of the momentum, the magnitude of the impulse, sorry. And then using right-angled trig, if you're lucky, or through using the sine angle, you have to calculate the angle and hence the direction of the momentum. And we can see that here. It gets pretty messy. So I recommend that you also revise angles on parallel lines, as that is very important. But we can just see very, very messy. And as such, this might be worth 6 or 7 marks, which is honestly 10% of your exam, should this occur in your exam. And then we also have some extended response questions on like the connections between Newton's third law and momentum and impulse, but basically just kind of memorize and understand this and you'll be all okay. External forces, remember we neglect friction and gravity because we assume that their effect is negligible on the system. And impulse time graphs, where the area under impulse time graphs is the force, the area under force time graphs, oh my gosh, talking for this long is not making me smart anymore. The area under force time graphs is the impulse, and then using the impulse, you can find things such as the initial velocity, the final velocity, the mass of the object, provided that you have those variables as we see here. That's essentially it. Thank you for sticking through this very lengthy recording. A little bit longer than I wanted it to be, but that's all good. yeah, if anyone has any questions, by all means, feel free to message me, and have a good night. We'll reconvene next time in class, and I hope to start Module 3 soon with you all.